Hello guys, welcome back to my channel. In this video I'm going to show you how to solve all parts for some problem. So this one belongs to depth first search pattern. So of course whenever you have a problem that mentions about parts, immediately think of using depth first search, right? So this one is pretty similar with the previous one we saw, which is binary tree part sum, right? You still remember it? In the previous problem, we also need to traverse for all the part and check if we have a part that sum up to S, right? But for this problem, the difference is we have to check down all the part that we have traversed and save all the part that sum up to S, so that we can return it as a result. So for example, let's go to the requirement. Given binary tree, so binary tree, we have two at max two child node, right? Left node and right node. Find all the parts from the root to leaf. So what is a leaf? Leaf is a node that has no child, such that the sum of all node values of each part equals to S, right? So it's same as previous problem. We need to calculate sum from the root node to leaf node. We check if it is equal to S, a given S, from the argument. So for here is an example. We have a binary tree of 3 levels. As you can see, we can have multiple parts. For this guy, we have 4 parts in total. First one is 174, 175, 192, 197, right? So among these 4 parts, there are 2 parts that sum up to S, which is our target in this case is 12. Target sum in this case is 12. So there are 2 parts that satisfies the sum up to S, right? Which is 174, total of 12, and 192 also sum up to 12, right? So yeah, for this problem, we're gonna use depth first search to traverse from root to leaf, right? So for depth first search, what is our order of traversing? For depth first search, we're gonna use from, in this guy, 174. Then we're gonna go all the way to the leaf first, right? Then we reaches the 4, which is a leaf node. We're done with one branch. We want on path, right? Calculate it, save it if it sum up to S. Then wanna come back to 7. At 7, right? At 7, we've done with 4 already. So now go to the left. Go to the left child, which is 5. Again, it's a leaf node, so we calculate the sum. After 5, we come back to 7. At 7, we've done 2 child nodes, which is 4 and 5. So we come back to 1. So at 1, we've done with 7, which is left node. So we continue with the right node, which is 9. Okay, we go to 9. Choose the left node first, which is 2. Okay, 2 is a leaf node, right? So we calculate the sum, then come back to 9. At 9, we've done with the left node, which is 2. The next is right node 7. We go to 7. It's leaf node, so calculate the sum. Done with 7. Come back to 9. We've done with 2 child nodes, right? So come back to 1. At 1, we're done with left branch and right branch. So we're done, right? So that's pretty much it about the order of depth of search. So maybe we can make it a little bit more clear by I'm going to record the call stack, the state of call stack, as we go through this example. So because we have to return the path, all the paths. So as we traverse the tree, we have to record the state. We need to store some state. The first one is probably the current path, right? The current path. For example, right, we are on. We will check is our current path is 1, right? We go to 7. We need to check it 7. We go to 4. Then it's 174, right? So we have 4. We are leaf node, right? So we calculate the total sum of the current node. 1 plus 7 plus 4, right? After that, as we come back to 7, we need to remove 4 out of actually we call it backchecking in technical term. So we're done with 4, we backcheck to 7, right? So we need to pop 4 from our current, right? So we go to 5, we push 5 to current again, calculate current, and probably we want to, because here it says that we need to find all the parts, right? So if we meet a part that sum up to X, we probably want it save it to our result. So later, after we've done traversing, we can return the O, right? So 2 pieces of information we need to store here, which is current and path. Okay, current and O. So okay. so I want to use recursions, right? So in order to in order to communicate between the function calls, right? We probably want to we probably want to have some way to some way to share data between recursive calls. There are different ways, but probably we can use it we can create a class, right? So the something like class of solution, let's say, so let's say the recursive call will be DFS, for example, right? So this one will be called recursively something like this.dfs, something like that, and so we should have a common data that that every recursive call can have access to. I'm gonna put it in constructor. So when we create an instance of solution, right, it has data, it has state, and it has functions. So anything inside this method can have access to the constructor, can have access to the properties, let's say. So we need two pieces of data here, which is all. It is what we will return from this one, and this dot current. We check out all the value from the root to the current node, right? Okay, so this one will return this at all, right? So down here, for this method, here's our main entrance, right? So in these functions, I'm gonna create a solution instance. I'm gonna call method dfs. Okay. Okay. This one will return all the parts, right? So I also need to return here. Okay. So we need the let's say what should DFS receive here is probably the current node, not current we use it here. So let's say root node, current, yeah, root node, and yeah, sum as well. Right. Let's say, okay. Here we need to pass in root and sum as well. Okay. Let's say, okay, we start to implement DFS method. Okay, when we're gonna start here is, okay, DFS here will take in root. This will be called recursively, right? So root here, root here is the actually the current node, right? That we are at, and the sum here is a target sum, from the current node to the leaf node, right? So it will be I probably want to show you the call stack as it is called. So the DFS method we first call, right? Let's say f. So the first call is will call with the root node is 1, and the sum, target sum at 1 now is 12, right? Okay, so we are here. We, after this is called, we probably want to check down the 1. We want to record the 1 to our current part, right? 1. Whenever we go to a node, want to check it to the current. Okay, so it's not a leaf node, so yeah, we look at left and right, right? So we can go to either left or right. Now we must go to left. Sorry, we must go left first, then right, but only if it is not null, of course. So here we are run. We go to the left first, which is, I'm gonna make a recursive call to the node that we pass here is a left of 1, which is 7, right? We pass in 7. Okay. At this node, what is the let's try to imagine. We try to kind of scoping down our problem, right? As we go down the tree. So we are as we are sending 1, we are delegating our problem to 7. So it's kind of like the node 1 is asking its left child, hi 7, can you find part the sum up to, can you find part from u, which is 7, to the leaf node, the sum up to what? To the original sum minus my value, because I exclude my value. So that you just need to you just need to care about the sum from u to the leaf node, right? So we subtract 1 from, which is value of the root node, from 12. Now we have 11. Okay. This again, it makes recursive call to for left node, right? Okay, we record 7 here. Probably, I think actually we can calculate the sum from the current part. So probably we don't need to check down this. We don't need this kind of piece. Let's say probably we can do something like okay, but probably here it will be a little bit optimized because we don't need to kind of recalculate if our tree is very deep, right? So if we do the calculations at the leaf node, right, we sum up all the value in the current, it's kind of not very performant. But if we passing down the target sum, right, we update the target sum and we traverse the tree, we will not have to recalculate, but we'll use reuse from the other recursive call. So this might be, so we will do this way, we still do this way, just okay. So F4 okay, the node 7 will subtract itself from the target sum, which is 11. So a smaller problem, which is if the node 4 sum up to 4, is the node 4 to the leaf node. Can we find a path from node 4 to the leaf node that sum up to 4? So here we checked out 4, right? So we are at root node now. So we can conclude that, yeah. So when we are leaf node and the value of the leaf node is equal to the current target sum, then the current path is valid, right? So we push it to the array, the result array, right? So as we done here, so because we are leaf node, so now there's no left and right, so we done here, so we pop it out, right? Also need to update the current, which is 1 and 7. Okay, so we come back to node 7. Now 7 have visited 4. Now it comes to 5, which is right node F5, and okay, the sum that we need here is still 4. of course in this case it is not valid, so we do nothing, we just pop it out again. Right, so 7 now is done because it visited left and right, so remove 7. So it's the same, the logic is the same. I will stop here so you can I think it's enough for explanation. Let's dive into coding. So okay, we have the root node here, right? So add, we go to a node. We want to save the value of the root node to current, this dot current. Push. Okay. Push what? Root dot file. Okay. After all the processing, I'm gonna return this at all. Okay. So we visit a node, which is root here. Let's go node. Okay, we push current value current node to the current. Okay. So we need to check if the current node is a leaf node, right? If this dot current it is a leaf node when it has no left and right. So this dot, oh, not this dot current, but not. Oh no, it's sorry. Not left, and we don't have node right. When that is the case, we want to check, right? If the sum equal to the value of current node, right? Which is node.val. It means we are at the correct, a valid path. So we want to push the current path to the, let's call it current path. Push current path to the O, but be careful because we want to clone it out. So later we will modify this array. So if we push current path here, it will be it will keep a referential pointer to the this dot current path. So it will not working, right? So I want to clone it down by spreading. Okay, let's create an array with the same values as current path. Okay. But if it is not a valid path, so whether it is valid path or it's not a valid path, if we are a root node, if we are a leaf node, we probably want to return. There's nothing to process here, so we return to the this parent node, right? And down here, if it's not a leaf node, it means this node can have left and child, either left and child, or both. So, what if we have node left, right? What we want to do here, we want to recursively call make a recursive call with node is a node left, and sum here will be updated to sum current sum minus value of current node. So we delegate the problem down, right? Node.val. So after we done with after we done with the recursive call, for example, we are current node, right? So we recursive call on the left. So after the control is given back to the current node, right? Then we want to pop out, right? Because as we traverse the, for example, the left, right? We will push the left value to the current path. So as we come back, we want to pop it out, which is current path of pop. Okay. Same for right node. If right is not no, go to right. Okay. Sum is the same. You don't get sum is the same here. So after we also need to pop it out. Okay, I think that's pretty much it. Let's run a test. Okay, works. So that's pretty much it. So thanks for watching. See you in the next video.